And I got to check the audio. Sorry, I didn't have my stuff all up. Okay, that's going. And here we go. Okay, so last time we were talking about Stokes' theorem. And remember the big idea with Stokes' theorem is that it's another one of these accumulation theorems. The whole is the sum of the parts. It's just that we have to specify what is the stuff. What kind of stuff is it that we're discussing? And after having made an appropriate definition of what we mean by boundary orientations, we made the observation that boundary circulation is an accumulating quantity. Sounds a little weird because, it's not something that we view as being distributed over the surface, but it acts just like it's distributed over the surface. Weird. So you can treat it as if it's a kind of a stuff. Correspondingly, you can talk about the associated density. The associated density, what I call circulation density, namely circulation per unit area, is computed by this formula right here. Curl dot normal vector, and that's the orientation unit norm. Okay, right. And then with that in mind, again, we have this particular stuff here, this quantity called circulation, which we abbreviate as previously with lowercase Greek letter sigma. We observe it's an accumulating quantity. We note that stuff is stuff per unit size times size. There's our stuff per unit size. That is our density. And we've got ourselves an integral theorem, a.k.a. an accumulation theorem. And there you go. All right, so now we make this observation, again, looking at stuff per unit size times size, expecting that this would remain sort of as the way I have it written here kind of vaguely suggests, a scalar surface integral. We came into this from the point of view of, stuff per unit size times size. Size is a scalar. But then you notice, neat observation, that the in part of the circulation density and the ds differential combine to make this vector differential that we've talked about previously, the ds vector. And so weirdly, it turns out that therefore, line integrals can be computed as a flux, which is not intuitively obvious. Right? This does not just leap off the page and, of course it is. No, nonsense, right? The fact that this is a flux is, I would say, unexpected. Okay. All right. So, example, and we did the details of this example last time, so I'm not going to go through it again. But the big idea here is to note that when you're asked for a line integral over a curve, some curve, what you need to do is to figure out how to view that curve as being a boundary of a surface. And in this case, thank you for that helps a lot. This is a boundary in this case, but you got to think carefully about the orientations. And again, orientations are a big deal. And I know it's just a minus sign in the answer, right? But it really, conceptually, it's very significant. And in order to view this as a boundary, the easy part is to observe that it's a boundary of that disk, orientation ignored. The significant part is to realize that it is oriented this way in order to make boundary orientations work out as they must if you're going to cite Stokes' theorem. Okay. All right, and then details we went through last time. Okay, so that's where we were. I hope all this rings some bells, and we're going to proceed along now. I'm going to go back to an idea that we talked about when we were doing the fundamental theorem of line integrals. This is just a recopy, pretty much, and maybe threw in a couple extra things. But all of this right here we saw when we were talking about the fundamental theorem of line integrals. That the stuff that accumulates in that theorem is change, and the whole is the sum of the parts, and there is an associated density, etc. Okay, so I'll further remind you that I took a weird point of view how this gets written down. The weird point of view was, well, look, if stuff is stuff per unit size times size, and specifically this is a scalar density being multiplied by a scalar size, right? All right, well then how would we view this statement here? How, if I kind of regroup things together, attach the t to the ds to make the dx, how do I interpret what I have here in blue? And the position I have on this, the weird take I gave you, is that stuff being something times oriented size. What is this? What do you multiply by oriented size to get stuff? And I think a reasonable take is to call this an oriented density. So it's just a take, right? It's just a sort of a point of view. It's an acknowledgement that dx is not just a size. Its magnitude is the size. It encodes the size, right? It's definitely clearly telling you something about the size. It's also telling you a little bit more. Right? And likewise, we think of the gradient vector as telling us a little bit more. Yes, the gradient vector tells us, how steep is the mountain. Of course it does. But it also tells us which direction is uphill. Which direction do you go to actually realize that steepness of the mountain, right? If the mountain's uphill is that way, if you choose to walk this way, you're not going to have that experience of the uphill that's how steep the mountain is actually is. So this tells you in which direction is the uphillness that magnitude describes. Okay, so the reason I remind you of all this stuff is that the analogy is bonkers strong when you try to make analogous interpretations about Stokes' theorem and curl. And let's see here, let me do this. So sure, you can say stuff is stuff per unit size times size, and this is stuff per unit size, all scalars, and this is size, again, a scalar. This, what you might call the scalar take on how density times size gives you stuff. So, okay, with that in mind, how do we view this equation? And recalling, as we just did, we sort of combined the orientation with the scalar differential to make a vector differential. Just like up here, right? We combined the orientation with the scalar differential to make the vector differential, right? Totally analogous move. So how are we going to interpret then this thing, right? This is the thing that let's see. Well, we're not multiplying by scalar size. We're multiplying by, again, this kind of oriented size. ds tells us, yes, how big is the piece of area, but it also tells us what is the orientation of that piece of area, just like the dx vector did for length. So if this is an oriented size, I think it's a reasonable take that we call curl the oriented density. Now again, that's just a point of view, right? It's a way to kind of familiarize, make sense out of this equation I have in light blue that is viewing little pieces of circulation as a dot product instead of a scalar product. But it has some really nice benefits, and specifically in the same way that viewing gradient as oriented change density allows you to interpret that, yeah, sure, the magnitude is the steepness and all, but the direction is how to maximize, how to actually realize that maximum value. The same interpretations work down here. Yes, the magnitude of the curl does tell you in some sense how we know curl is talking about a rotation of the fluid, but keep in mind fluids can rotate in a lot of different ways. around a lot of different axes in space. So the magnitude may tell you how much of a rotation there is. The direction tells you around what axis that's happening, in some sense. So very important interpretation to take there. And this point of view, calling it oriented circulation density, the orientation, putting in the oriented term here in this phrase, indicates that the direction of that vector, the direction of the curl vector, is telling you, in some sense, in what direction that's happening. Okay, so here is just a kind of a quick picture of how to visualize that. And you have a curl vector, sure, right? And yes, the curl vector has a magnitude, right? Again, the magnitude tells you, in some sense of the word, how powerful is the tornado, how much of a rotation of the fluid. Don't worry about the units, right? Units are somebody else's problem. But more magnitude means more circulation, more rotation of the fluid. And then furthermore, the direction that it points, the direction of the curl is telling you around what axis is that rotation happening. Does everybody see what I'm describing here? These two interpretations that you get from the curl vector. How much of a rotation and a rotation around what? Okay. All right, so just a very quick, let's just observe that this actually kind of works. This is just a differential scale. Imagine this is a teeny tiny little piece of surface here, and we have a fluid rotating in a very convenient, world's simplest rotation, right? Let's not consider complicated cases. Just literal rotation around an axis. And notice the extent to which the fluid, hang on. I wanted to be in highlighter mode here. The extent to which the fluid is going around that boundary, right? To what extent do we have actual circulation of fluid around the boundary? I'm just geometrically, I'm going to say, yeah, quite a bit. I mean, that fluid is literally going in the direction the boundary is, kind of in some sense the whole way around. We would expect to have a significant amount of circulation around the boundary of this little piece of area. And notice that as it should, this is detected by the curl and the orientation normal having a significant dot product, right? The fact that, geometrically, the fact that the rotation is around the boundary is not coincidentally simultaneous with the curl and the normal pointing in the same direction. Right? And just by contrast, what does it look like when it doesn't happen? What does it look like when the circulation is just totally different direction? So here we have a circulation of fluid, but the boundary it's just going a different way, right? To what extent is this fluid doing like this? To what extent is that fluid going around that? This boundary is turning in a totally different direction. We wouldn't expect there to be much circulation on the boundary of this little piece of surface. This circulation is going a different way. So basically not much circulation, and that is again tracked perfectly nicely by the fact that that dot product is not going to be very big either. Curl dot in, those vectors are pointing totally different directions. So not much circulation, tracked by not much dot product. Okay? So this is just a plausibility argument. This is just to give you some sense for how this expression, right, curl dot in, is measuring, effectively this circulation density that we talked about. And furthermore, to give you some sense for what we talked about here about how to interpret curl. Again, curl points in the direction of the effective axis that the rotation is around, and with a magnitude describing how much of a rotation there is. Okay, so just a sort of geometric, sort of qualitative, take. All right, a couple of quickie observations. By the way, I'm sure you've noticed we have today is our last day for covering Chapter 7 material, and there's quite a few pages left. So let me take a quick pause and point out that a lot of what I have in the Chapter 7 notes is supplemental stuff that I like to be able to cover when time permits and is not really essential. Some of it's not even officially part of the course, and it's just, I just want to tell you all stuff that's going to help you in your future, and I think will be useful. And likewise, a lot of this stuff is also perfectly readable, and you can, read it on your own. So I am going to be going quickly through some of these things. I'll try to be very explicit about what you should read and what you're just not responsible for. Anyway, and we're gonna make it just fine. There's nothing to worry about. Okay, so back into it. We have previously observed that curl is telling you the nature of the rotation that's sort of implicit in a vector field that describes the velocity of the fluid, or either velocity or velocity times density, depending on the context, and again, different interpretations. So curl is a way of measuring, to what extent, again, my favorite metaphor, if you drop a little leaf in the on the surface of the little stream whose motion is described by that vector field, how will that leaf rotate? And I think it's a pretty easy pitch that you look at how this water is flowing here, and it's flowing faster on the, what you might call the bottom side, and so, it's being pushed harder on that side. This leaf is going to rotate counterclockwise. And if you were to write down a formula for this vector field, and if you were to compute the curl, you would get a positive result, because positive means counterclockwise, which again we see in the picture. So totally analogously, in 3 dimensions, and again we use the term curl. It's one of these things. The word curl means something in 2 dimensions, and it means something similar in some ways but different in some ways in 3 dimensions. Anyway, curl again is telling you about the implicit rotation, and if you have a fluid that's rotating around in some way, as I've tried to draw here, and this time let's imagine sort of perfectly weighted, perfectly buoyant balloons with just that right amount of helium inside, to where they don't just fall to the ground and they don't just go straight up to the ceiling. How will such balloons be rotated by the movement of the air, being our fluid in this picture? And the curl tells you what axis those balloons are going to be rotating around, and in some sense how fast they're going to be rotating. And again, longer means faster, and let's not worry about units. That depends on friction and various other considerations. Moment of inertia of the balloon. Details, that's not a problem. Longer curl, more rotation. That's what we're aiming for here. Okay, so I hope this is a believable interpretation. This is totally analogous to the take we gave on 2-dimensional curl, and nice little metaphor. Let's see if I can get that. Okay. So now this physics stuff here, this other physics stuff here, magnetic fields is one of these things that we just don't have time for. This is not part of the course. I don't think it's even in the book, if I remember correctly. I don't remember for sure, but I don't think it is. Certainly, it's not something that we're going to make part of the course. So you don't have to look at this if you don't want to. That said, this is in your physics future if you're an engineer, or it might be in your physics past, I suppose, depending on when you took which courses. But it's a pretty neat thing to know, and I'm going to be super quick, but if you have a flow of charged particles, that's what we call a current field, right? Just a fact of the physical world is that this creates this thing called a magnetic field, represented by the letter B. I don't know why. And this magnetic field B and the current field J have a couple of really strong relationships. And here they are. One take on it is this. The other take on it is this. And again, you'll notice a little square of equations. You may recall that I made a similarly arranged square of equations when we were talking about gravity and electric fields and electric charge and all that kind of stuff. And mathematically, the analogy is quite strong, but again, we don't have time to go into the details. The point is, you get two different takes on the relationship. And again, the big theorem is what makes the connection between them. The thing that makes this conclusion possible, to note that these results are effectively the same result, comes out of Stokes's curl theorem. Stokes's curl theorem is the connection between these. Okay, in a very similar way. All right, more time than I had intended to spend on that. Okay. Flashback. Chapter 6. Neat theorem, what I call the local test. The local test in 2 dimensions is that if you want to know whether something is a gradient or not, then curl is the thing to look at. If the curl is 0, then yes, it's a gradient. If the curl is not 0, then nope, it's not a gradient. It has no anti-gradient. Don't look for the anti-gradient. It's not there. All right, so handy little test. And again, the thing that made this work, various observations to be made, but Green's theorem is, again, one of the critical sort of doing the heavy lifting, you might say, in this argument. That's the thing that allows you to take discussions about line integrals and turn that into a statement about a double integral. And so again, the power in this argument comes from Green's theorem. Then I made an analogous statement about, let's see here, what did I use for colors? Purple, yeah. Okay. I made an analogous statement about how do you tell if a 3-dimensional vector field is or is not a gradient. And the answer was, you look at, well, again, curl. Now, again, different formula in 3 dimensions. It's a vector. It's computed, by a formula that cosmetically at least looks like a cross product. But anyway, still call it curl. And whether that is 0 tells you the answer to the question of whether your vector field is or is not a gradient. Does or does not have an anti-gradient. Should I or should I not search for such an anti-gradient, right? All resolved by just computing curl. And when we made this statement, I kind of said, well, there's good reasons for this, but we don't have the tools. There was a missing theorem that we did not at that time have to work with, and we now do. And it is Stokes's curl theorem. And you'll notice where it sits in sort of the layout of these arguments. Right? Totally analogous in the layout of the arguments. Stokes's theorem is the 3-dimensional version of Green's theorem that we need to draw this 3-dimensional conclusion about how to arbitrate, is there an anti-gradient or not? And, why is it that curl answers that question for us? Okay. So as y'all know, I'm a big fan of analogies, and this is another pretty good one. Okay. Now, on to something new. And this is something I am going to try to focus on, because I think this is really important. I think this is a really powerful idea. And this is basically not in the book, if not entirely not in the book. And again, there may have been a passing comment, but this is at a minimum undersold. And by the way, not rare. In my personal opinion, very few, if any, multivariable calculus textbooks talk about this. And it's super important. And I don't know why they don't talk about it, because it's super useful. Anyway, here we go. So flashbacks to path independence. I'm sure you all remember this idea called path independence. What does it mean for a vector field to be path independent? And just a reminder, it says whenever you have two curves, C1 and C2, that have this, I didn't get the C2, that have the same boundary points. In other words, they start at the same point and they end at the same point. Right? So two curves with the same boundary. A vector field is path independent if the resulting line integrals are always equal. Right? And again, reasonable term, right? Which path you take between the agreed upon starting point and ending point, which path you take doesn't even matter. Right? The value of the integral is independent of what path you take. That's the term path independent. Okay. And then recall there's a different take, which is that a vector field is path independent if, when you look at the closed line integral going all the way around, as you might say, sort of C1 minus C2, right? Positive direction along C1, but then backwards along C2, if that integral is always 0. So, I hope everybody remembers this path independence. Okay, so something totally analogous works for surfaces. So we're going to talk about what does it mean for a for a vector field to be surface independent. And by the way, in the same way that path independence is a property of the vector field, likewise, surface independence is a property of the vector field specifically. It's about the vector field. And what it says about the vector field is that, again, in this scenario where we have now a surface and another surface that have the same boundary. Now, let's think about this. These are surfaces, not curves. Their boundaries are curves, not points. So I need these two surfaces to have the same boundary curve. Right, so sort of imagine, if you will, the scenario I'm portraying. Here's a surface, same boundary curve, right? In the same way that the edges of my hands are fitting together here to sort of enclose maybe I caught a firefly or something, right? In the same way that my two hand edges are the same curve, right? Likewise, that's what we're talking about here. And in this scenario, what does it mean for the vector field to be surface independent? It means that that vector field has the feature that the flux through the one surface and the flux through the other surface are always equal. Or alternatively, if you prefer, totally analogous, a vector field is surface independent if, when you look at the entire boundary, in other words, the whole, both of the surfaces, again, oriented one opposite so that In fact, it is a boundary of the solid in between, that the closed surface integral, that boundary flux, is always 0. So now, again, the analogy is super strong. So look at and I think the colors do a great job here of underscoring. You look at what we've said about path independence, what we've said about surface independence, and I've color-coded with the goal in mind of emphasizing which players are analogous to which other players in which story. And notice how the colors lay out exactly the same, right? And this is really, really strongly analogous. So, 2 seconds. When you're trying to digest the idea of surface independence, think about path independence and think about how, what happens in path independence? What is the one dimension higher analog of that? And that's your suggestion of what to expect when you're thinking about surface independence. Yeah?
Why is the normal vector in S2 oriented upward?
Yeah, so, this is a delicate point here, right? But so notice over here, I'm saying that S1 and S2 have to have the same boundary, right?
Okay.
But remember that boundary is an oriented thing. And so if you play the geometry through and just kind of think about the, swirls and all of that, if S1 is oriented as I have drawn here, and if S2 has to be oriented such that it induces the same boundary orientation, it has to be like this. So in some sense, outward for 1 requires that you do inward for 2. And that's just, again, play with the geometry. Think it through, right-hand rules and swirls and all that. That's just how it works out. Again, totally analogous to up here. If you think about it. C1 and C2 both go the same direction in the sense that they have the same boundary starting point and the same boundary ending point. But notice C1 is counterclockwise, and C2 is clockwise. So that's just a kind of an oddity of how geometry works. It's a great question. I wish I had more time to go down that bunny hole, and there's a lot of fun ideas there. Okay. All right, so very analogous result, very powerful result, and I hope y'all will, again, focus on the analogy there. I'll further remind you, when we were talking about path independence way back when, I made this cool observation that all gradients have that feature. And you can flip back through Chapter 6 notes and find where we made that observation. And the tool that we used to prove that was the fundamental theorem of line integrals. Well, as it turns out, there is an analogous true statement about surface independent vector fields, and that is every curl. Well, you got regularity issues. It's got to be continuous. Not our problem. But every curl field, like so, is surface independent. And it's, again, a pretty easy observation from the following application of Stokes' theorem. So I apply Stokes' theorem here twice. The flux along the first surface, let's see, let me try to be consistent. The flux through the second surface. Stokes' theorem says that if you're talking about an integrand that is a curl, if your integrand is a curl, then you can compute the flux of curl by a line integral around the boundary of the what you might call the anti-curl, right? So boundary line integral of the anti-curl. And, well, the whole point to surface independence and comparing these two fluxes is that these two surfaces have the same boundary, and if they have the same boundary, then, of course, we're going to get the same value in computing this line integral, and that means that the green flux and the blue flux have to be the same. So, again, totally analogous. Again, I hope you'll flip back through the notes or rewind to the appropriate spot in the appropriate video from when we talked about this for path independence. This argument is totally analogous. Yeah.
I'm a little confused because I thought
Yes.
for path independence we said that it had an anti-gradient and like it was path independent if the curl was 0.
Correct. For path, yes, that's right. And there is an analogous fact about surface independence. So yeah. So let me. Okay, I'm going to switch, by the way, to a different screen. Let me switch over to our diagram. What you said is totally true, and let me diagram that out. If you have a vector field and you want to know, is there an anti-gradient, that the way we detect that is by looking at the curl and seeing if it's 0 or not. Right? Okay. So, yes, absolutely. So what is the analogous, what would we expect the analogous statement to be in this new context? Well, if we were to slide everything over, and if I were to ask, okay, now I'm looking at vector fields, wrong color. I'm looking at vector fields, and I want to think about vector fields that I'd compute a flux of, and hey, is this vector field surface independent? Is it a curl of something? We're going to arbitrate that, but it's not going to be by way of whether curl is 0. It's going to be by way of whether divergence is 0. Does that make sense? Yeah. No. Correction. What I should have said. My hope is that you would see here why we wouldn't expect curl being 0 to arbitrate the question, right? Curl is the thing I'm trying to figure out if there's a way of undoing. Yeah. It is very easy to get confused on this kind of stuff and to get disoriented, and this is one of the massive advantages of this diagram, which again, not in the book, which kind of blows my mind. This will keep track of these ideas for you. Yeah. Absolutely. And I'm going to expound on that in just a bit. Okay. So Stokes's theorem, let me do this, tells us that every curl is surface independent, regularity issues aside. And it also true, harder to prove, not something we have time for, wouldn't be appropriate in this course anyway, but not only is every curl surface independent, every appropriately regular surface independent field is a curl. So they're synonymous. In the same way that gradients and path independence, simultaneous, all the same vector fields. Likewise, curls and surface independence, simultaneous. They're the same vector fields. Different features of the same special fields. Okay. Yeah. And y'all will recognize this little layout. Whoops. Local test. Want to figure out how to know whether something is computed with one of these operators. There's a thing that you can compute and see if it's 0. I mean, it's just like the local test we saw previously. This time, though, a little different. And we're interested in not whether f is a gradient. We're interested in whether f is a curl. And it turns out that divergence is the right answer. Now, we kind of expect this result from the diagram. The little diagram argument that I gave you kind of suggests that maybe, if the analogy were to hold, then that's what it would kind of have to be. So, but I am not saying that we would expect this to be true. I am saying this is true, and here's the argument. We already talked about how these things are all equivalent. Every curl is surface independent and vice versa. Surface independence means closed fluxes are 0. And this argument right here is, again, not such a hard one. If there is some function, divergence in this case, but if there is some function whose triple integrals are always 0, how could that be? How could triple integrals, for no matter what solid region you're talking about, the triple integrals always 0? Come on, how could that be? That thing itself has to be 0. And the thing that brings these two together, the thing that relates closed fluxes, boundary fluxes, with a triple integral of divergence is Gauss's divergence theorem. So, I mean, it's a different big theorem that makes the connection for us, does the heavy lifting, as it were, but this is the analogous local test that if you want to know if something is a curl, more likely, if you want to know if something's surface independent, take the divergence. See if you get 0. If you get 0, yep, that's a curl of something. I don't know what, but it's a curl of something, and more to the point, your vector field is surface independent. Okay, so this is a very powerful result. Let's see how this works out with this example. So we've got here a vector field and a surface, and we want to compute a flux. Let's just for clarity's purposes, let me note that my surface here, it's part of this elliptical paraboloid. So it's this surface here. Very important little landmine. A lot of students step on. Please be heads up for this. This part down here is not included. What you're going to be tempted to call the bottom face is not part of S, right? So all of this discussion here, with z greater than or equal to 0, that's just specifying which part of the paraboloid we care about. We are not saying, and it is not implied by that language, that, the part where z equals 0 is also included in S. That's just not what it says, right? So, again, be very careful with the landmine. You do not include this bottom piece of the surface. That's not what the language says. Careful. And with that noted, again, we've got this surface S. It's like this, and we want to compute the flux of some vector field through that surface. How are we going to do that? How are we going to compute that flux? Well, golly, I guess we could do it the brute force, the old-fashioned way, right? We could parameterize. I guess in this case it wouldn't be that bad, but my imagination can definitely see how this could have been a different vector field, and this could have been a much uglier vector field, and this could have gotten ugly. Right? Brute force computation here in a different scenario could be super ugly. Okay, so let's call that plan B. Can we use Gauss's divergence theorem? Is this surface a boundary? Nope. It's not a boundary. It's just not. Again, it's open at the bottom. This bottom piece of surface is not included. So Gauss's divergence theorem, not really on the table. Now, here's a fancy take. This is asking for a flux. Maybe I could use Stokes' theorem. But just keep in mind, Stokes' theorem requires that I know what this F is a curl of. I would need to find the anti-curl. And you may have noticed, I haven't shown you any methods for finding anti-curl. And that's because it's hard. It's not really something that's that you can just kind of crank out. So that's not an option either. So surface independence is our only, what I'm going to call, realistic tool for addressing this in a convenient way. And like path independence, you can't just go around claiming it. You got to show it's true. It's definitely not true for all vector fields. So we got to earn it. If you want to conclude that something is surface independent, you're going to do so by computing the divergence, confirming that it's 0, and then declaring victory. Hey, yeah, check it out. We've met the requirement. This vector field is surface independent. So you'll notice that's what I do here. Right? I say we're going to take this vector field here. We ask what is the divergence. I compute it and confirm that I get 0. And then I declare victory. This vector field is surface independent. It is a bonkers powerful conclusion. The beautiful thing about this to me is that the computation here is pretty easy. Right? The actual, like, what's the cost on your end? Right? Pretty easy calculation, divergence. Just a couple of partial derivatives and a little algebra. It's not that bad. And you get this really powerful conclusion. You're invoking big, powerful ideas, sophisticated, heavy-duty Math219 heavy ideas, drawing powerful conclusions at very little cost to yourself. So this is something you want to make extra sure you're very comfortable with how to do this, because this shows a lot of understanding of what gets you points on exams. Right? So make sure that you're comfortable with that. And then we just have to think through, okay, how do we use surface independence? The surface that we have is this thing. Let's remind ourselves what surface independence requires. Surface independence requires, if I'm going to apply it, that I look at a new surface that has the same boundary curve. Got to be the exact same boundary curve. So, fine. Let's come down to here. This surface has a boundary curve. That's this ellipse thing down here in the xy plane. And if you think through the right-hand rule, keep in mind this surface is oriented downward, and thumb in the direction, and swirls and all that. This boundary is oriented that way, which you might call clockwise, as seen from above. And so what surface has that same boundary? Well, there's a million of them, right? You can pick that surface if you're just looking to make your life difficult, or something like that. All sorts of weird options. Why would you do that? But the obvious, easy choice is this solid ellipse in the xy plane that has obviously the same boundary, right? And if you play orientation games, again, thumb and swirl and fingers of your right hand, etc. This has to be oriented downward to make the orientations work out. So we observe surface independence. We find an appropriate new surface to think about, and the computation crumbles into triviality very conveniently. On this original surface, the integral is hard. Now we're going to consider instead the integral on that new surface, and I claim that that's easy. Right? So thank you, surface independence. Surface independence is the thing that allowed us to do the big, again, heavy lifting change to argue this surface gives me the same answer as that surface. And now you just have to compute, and it's an easy computation, really, because we already know our normal vector. And you plug that in, do the dot product with the vector field. The dot product ends up being this. Easy. This is a scalar surface integral. We cite a symmetry result. Bada bing, bada boom. We're done. Everybody see how that worked? Details for y'all. Think through the dot product. Think through the symmetry argument. But it works out really nicely. Okay. All right. So real quick, super quick. This right here is just a mention, sort of a reminder of how the pattern on the diagram holds so strongly. I actually went through a lot of that back in Chapter 6. Be nice if I had a chance to do it again, but time didn't work out. The next 6 pages are sort of supplementary examples that, again, when time permits, I enjoy being able to go through and show you how to sort of strategically go through and compute line integrals and surface integrals out of context, right? So that, like if you're in the section on the divergence theorem, you kind of know the divergence theorem is going to be the tool that's going to, right? But if you're not, if that contextual giveaway is not there, how do you know what theorem to use? These examples discuss how to make those decisions. What I'm going to do, since I didn't have time to show you these examples, is I'm going to share with y'all some recordings that I made couple of years ago. I think it was during COVID. Yeah, it must have been. Anyway, where I will go through in these videos all 6 of these examples, and you can see all the details of how to use that diagram to diagnose and solve. And we're done for today. And see y'all on Wednesday. Have a good one. Welcome back. Hope everybody had a good break, by the way.